All right. Happy Friday. Confession time. Your tests aren't marked. Not even a little bit. I said, oh, thank you. And then I put them here. And then I had to do other things. You know what? That's an option. And it's always tempting, right? No, you'll get them back on Monday. As soon as I'm done marking, I post the grades, so you'll know when I'm done. And it looks like it's not official yet, but the final exam schedule is being posted today. Should I tell you? No. You want a surprise? Oh, isn't she so cool? Our final exam, last I heard, and it stayed stable over the past 2 drafts, so I'm feeling pretty confident, is on December 15th. I guess at 9, well, from 9 to 12. Nice time slot. Morning time slot. It's not the 6 to 9 one. That's nice. So December 15th. I think that's a Friday. Yeah. And today's a Friday. So it's only a number of Fridays away. So that's a longer time slot, meaning that there's more content. It's the entire course. Yeah, and then it'll probably take you as well. I try to make it a 2-hour exam so that you have time to kind of think about stuff, but it is the entire course, so there's quite a bit of material. You can have 3 hours, up to 3 hours. Yeah, you have the 3-hour block. Yeah. It's a 3-hour slot, but I try to make it a little bit like a 2-hour, and then you kind of have some wiggle room. Yeah. Maybe 2 hours and 15 minutes. Really pushing the boundaries there. Okay, so let's see here. I'm trying to remember what we did last day. It was the test. But before that, we started polynomials. So let's review polynomials. I feel like the review is going to take half the class today. That's okay. It's been a while. Polynomials are when we have things like f of x is a subscript n times x to the power of n. Right, we use that a subscript n just to denote the coefficient of x to the power of n, okay, plus a subscript n minus 1 to the x to the n minus 1. And then it keeps going, ... all the way to a2. Let's pick up at a2, x to the 2 plus a1, x to the 1 plus a0, x to the 0. But what were some things that we highlighted? We said, okay, let's remember that x to the power of 0 is just 1. So then I can replace a0 times x to the power of 1 with just a0, right? There's a constant there. And also x to the power of 1 is just x, so usually we don't write the power of 1, but sometimes I write it to emphasize that it's still there and it does match the a subscript 1, right? And what were some other things that so let's rewrite this in the simplified form. F of x is a subscript n, x to the n plus a n minus 1, x to the n minus 1, plus a2, x to the 2, a2, a1, x plus a0, right, is usually how we end up writing it. It's another thing we said, we try to write them in decreasing powers. Why? Because the degree of the polynomial is the highest power in the polynomial, right? And so here, let's say the degree of the polynomial is the highest power. Why was that useful? That was good to know because the degree of the polynomial determines the end behavior, right? And so, let's see here. The degree determines the end behavior, which is where we kind of spent a lot of time, right? In general, if you have an even power, then the end behavior looks like what? It resembles x squared, x to the fourth, x to the sixth. They all look the same, right? And so as x goes to infinity, f of x also goes to infinity. And as x goes to negative infinity, f of x goes to infinity. If you have an even power, what's another condition with a positive leading coefficient, right? An, if it's positive, it means it's facing up. If an is negative, then it's facing down, right? And so then we're also looking to here this leading coefficient and if an is greater than 0, it can't be 0 because then our degree is n minus 1 and it just makes a mess. So I'm not going to talk about 0. Then you just have to step down and it's no longer your highest degree. So what a mess that would be, right? Whereas if you have an even power with a negative coefficient, an is less than 0, right? Then it flips it down, and depending on how big your polynomial is, there can be a lot of activity in here that we're ignoring, right? And maybe I shouldn't draw the whole thing. Maybe, just maybe, I should be doing something like this. It's unknown. Right? But, oh, how cute of me if I could do a dotted line. How? I used to be able to. I'll just do it by hand. Do, 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 do. I should do the same. Right. Just to emphasize that we're just talking about the end behavior. Now here, as x goes to infinity, f of x goes to negative infinity. And as x goes to negative infinity, f of x again goes to negative infinity. Not very nice infinities today. You'll survive. Tough nurse. Okay, this one is really bad. I'll fix it. Okay, and this one is really bad too. Oh, nice. On average, they look really good. Okay. What if we have an odd power? Then whoop, we've got this like this. Which means that as x goes to positive infinity, f of x. Okay, so now I'm heading out on the positive x-axis. It's going into the positive infinity. Oh my gosh. They look like pancakes. Fine. Ooh, nice. As x goes to negative, and okay. I need to have a really nice infinity that I just copy paste. You want me to do what now?
Yeah, exactly.
It's all fun and games when it's huge. Let's see. It does make you focus on the curvature more. Here, I'm just sloppy. Okay, I'll try it. F of x is going to negative infinity. Got so caught up in my infinities. That looks too bulbous for me. I don't like it. Looks like eyeglasses. It does look better. It's just not how I'm used to seeing my infinities. All right. What if, again, so this is only if the leading coefficient is positive, right? What happens if it's negative? It flips it on the x-axis, which means that this little guy is going to be flipped up here, and this little guy is going to be flipped up here. Which makes me think my sister a long time ago used to be a chemistry lab TA, and her reviews, so you know how you write like reviews, whatever, teaching reviews, she was reading them, and a lot of them were, oh yeah, but I wish that she would use proper terminology instead of like this little guy and this little guy. You just take this little guy and you put it in this little guy, and then this little guy comes over here. So that's what we had that posted on our fridge for the longest time. It's really funny. So I shouldn't say that. This little guy flips over here. This little guy flips over here. So critical this morning. Still looks bad. Tiny arrow. How's that? Thank you. As x goes to, okay, here we go. Infinity. F of x is going to go to negative infinity. It's taking all my strength. As x, there, I did it. Can't teach an old dog new tricks. As x goes to negative infinity, f of x goes to positive infinity. And on a high note. Nice. Okay. So a lot of the information about the polynomial is going to be from this leading term, right? Each kind of chunk of things are terms, right? And so this here is your leading term. And then this is just the term. And they're all just terms. Huh? Okay, that's pretty cool. So we can look at anything, any polynomial. It can be huge, and we can know the end behavior, right, as x goes into either infinity. That's nice. All right. Now, where was I? I need to look back and see Haha, I even set us up. Nice. I'll do this. I'm going to snag this and bring it in so that we have it. That way we'll have it. There. So the next thing that we're going to do is, so we've talked about end behavior of a polynomial. Now we're moving on to the zeros or the roots or the horizontal intercepts. Those are all the same thing, right? And so the horizontal intercepts are where it crosses the x-axis, right? And so they're also called zeros or roots. And we are familiar with the vertical intercept, and that's when x is equal to 0, right? What's the output when x is equal to 0, right? And then, so that one's usually pretty easy to find, right? You set x equal to 0 and you evaluate the function, and then that's your vertical intercept. The horizontal intercepts, that's where we require a little bit more work, because what do we have to do? It crosses the x-axis when f of x is equal to 0, right? When the output is 0, then we have the horizontal intercept, okay? And so we need to find what values of x produce an output of 0. For polynomials, there's usually more than one thing that makes it 0, right? It's allowed to cross over lots of times, right? So there's all those would be horizontal intercepts. Okay, now we're ready to do what we do. Hey, where is it? There. Make this a little bit bigger. I'll call that, oh, question. Online. Don't know. Call that the end of the review because we didn't do this. But here we go. So I like to find the vertical intercept first because it's the easiest. Get it out of the way. Why not? Right? What do I have to do? I have to evaluate the function at x equals 0. So the vertical intercept g of 0 is 2 times 0 minus 1 times 0 plus 3, oops, times 0 minus 2. 2 times negative 1 times 3 times negative 2. Multiplying those negatives is going to make a positive, and then I have 4 times 3 puts me at 12 often, right? It's early. Okay, so then now I know where it crosses the y-axis at y equals 12, right? So x is 0, y is 12. That's my vertical intercept. So in terms of my graph here, I would cross, if this was 12, then this is my vertical intercept. Can you have more than one vertical intercept? No, right? Then it wouldn't be a function, because what would that look like? Well, I mean, you can, but for us now, you can't. What would it look like if you had something like this, right? Then you could have multiples, but for now, we can only have one. Okay, now onto the hard part. Well, it's not hard, it's tedious. We want to find the values of x that make the output 0. And so I'm going to write g of x is equal to 2 times x minus 1 times x plus 3 times x minus 2. it's tempting to expand that, but what we'll see is that it makes it a lot easier to find the horizontal intercepts if it's set up like this, okay? And so what I want to do is I want to force this to be 0. And maybe what I should do instead is write it like this: g of x is equal to 0, instead of having it across the page like that. Do this. Right? Replace g of x with what it actually is, still equal to 0. Now, if I let x be 1 here, 2 times 0 times 4 times -1, well, I've multiplied something by 0, so it doesn't matter what the rest of the terms are, right? This whole thing is going to be 0, right? If I force one of these to be 0, right? And so now, if I let x be 1, g of x equals 0. That's good. Now I'm going to parking lot the x minus 1 term and move on to the x plus 3 term. I can do the same thing again, right? What if I let x be -3? Now -3 plus 3 makes 0. So something times something times 0 times something is always just going to go to 0, right? And so now I'm just forcing each term to become 0, right? Yes.
Back to the yellow part up there.
Oh yeah.
How do we get equals 12 there?
I did 2 times -3 times, or yeah, I guess -3 times -2. That wasn't, I didn't say that properly.
Oh,
2 times -1 times 3 times -2. Yeah. So we're just multiplying across. Okay. Now, finally, we do the same thing for this term, right? Looking at x minus 2, if I have to force it to be 0, then I let x be 2. So then here I'm going to let x be 2, which also makes g of x equal to 0. What does that mean? That means that we have 3 horizontal intercepts at x equals -3, x equals 1, and x equals 2, right, in the proper order. So now I've got pretty good idea here. If I have 12 here and I have, let's see, that doesn't look like a 3, -3, 1, and 2. Okay. Looks like we could almost sketch this thing, right? What would we need? We'd need to know what the leading coefficient is, right? And probably the entire leading term would be helpful, right? But if I have 3 x's, right, when I expand this out, I'm gonna get x to the power of 3 as my highest power, right? And so x to the power of 3, that looks like this. Okay, so the end behavior is going to be going to infinity and -infinity. I'm taking it a little too far, but I think you can handle it. Like this. It's where we're heading. It's what's for dinner. No. What's that a commercial for? It's what's for dinner. Is it just beef? Okay. Yeah, no, it sounds like it. Oh, really? It's what's for dinner.
Oh, yeah.
Oh, wow, that's, I'm gonna say weird, yeah. Yeah, not that cute, but I feel like you can do better. It's a cat. They're super cute. Yeah. Okay, so if you had to guess, knowing what your bookends look like and knowing that you have to cross through these points in some way, in some continuous way, what's a reasonable guess at the shape of this thing? All right, here we go. I'm going to use dotted lines because, like I said, we're going a little, that should be more of a curve like this. I'll change it. I wasn't going to take it this far. There. And then what can I do to cross at 1? And then I might have a little dip here. Who knows how far? And then join up. Nice. So knowing where the intercepts are, right, we'll be able to figure out what this graph is supposed to look like. Okay. Knowing what graphs are supposed to look like isn't super important, but it is good for being able to check to make sure that your answers make sense. And right, if you were able to, if you had found, you know, maybe some intercepts that didn't make sense, if you sketch it and you can't get it to join up, then maybe something went wrong, right? So that's why I'm bringing it up, but pretty fun. That's elaborate. You can do it. Wow. All right. Let's see here. Hey, that's the one we just did. Okay. As a fact, copy. Like I said, I did go a little bit further than I was supposed to today, but in the end, that's where we're heading. Okay. So here, a polynomial of degree n will have at most n horizontal intercepts, right? We said, okay, if I have a degree 3, then at most I'm going to have 3 intercepts, horizontal intercepts. Okay. What would it look like, or what could it look like if you only had 1 intercept or horizontal intercept? You could have it going through here, and then this could do a little U-turn before hitting the x-axis. That's possible, right? And then you'd only have 1. Could you have 2? Yes, if you had a different degree, I guess. Right? That kind of thing. Okay, so an odd degree polynomial will always have at least 1, right? As we saw, because it needs to send 1 down to negative infinity one way or another, or send 1 up to positive infinity, but it doesn't have to do both, right? And so it'll have at least 1. And a polynomial of degree n is going to have at most n minus 1 turning points. What's a turning point? Well, here I force the intercept to be the turning point. That's not necessarily the case. It's just the easiest way to think about it, right? So here's a turning point. Here's a turning point. All right. So let's see here. So we have 2 turning points for a degree 3 polynomial. It all checks out. Okay. Good. Where is it? Oh, it's not what I wanted. I wanted another example. So knowing that, we can answer this. Riddle me this. What's the least possible degree of the following graphs, right? And so knowing that you're going to have a polynomial, I'm not used to you guys seeing my pen situation, different rooms, whatever. So a polynomial of degree n is going to have at most n horizontal intercepts, okay? And of course, an odd degree, which we'll know by the end behavior rather than the intercepts. But an odd degree polynomial will always have at least one, and we're going to have at most n minus one turning points. Okay, so we want to know what's the least possible degree of these graphs. Okay. And so, okay, the end behavior looks like an odd degree, right? And so we can start there. Looks like an odd degree. It can't be, let's see here. I have two turning points. Two turning points. And I have 1, 2, 3 horizontal intercepts or roots or zeros. They all mean the same thing. So going by this, if I have at most n horizontal intercepts, it can be a power of 3, right? That's satisfied. It can't be a power of 1. Why? Because a power of 1 just is a straight line, right, on the diagonal. And so that's we know that. So then the next lowest one that we have to play with is x to the power of 3. And now I'm just making sure that n equals 3 is satisfying these criteria. Okay. So at most 3 horizontal intercepts, right? And so here I'll put n equals 3 question mark. And then we're going to check to see if that's true. It is. Because I'm allowed to have at most 3 horizontal intercepts, which is satisfied. If I had more, right, then I would have to have a higher power. Okay. And at most 2 turning points, so 3 minus 1 turning points, I've got 1, 2 turning points. And so, therefore, the degree or the lowest, the least possible degree is 3. This is one of those scenarios where the vertical intercept is 2, but it doesn't arc at 2, right? When I was sketching my graph, I like to make it go through the vertical intercept, right? But it can be off to the side. It doesn't have to look like that. And so it can look like that. Don't worry, we'll have a way of finding those local maximums and minimums. Just you wait and see. Not flying blind. Okay. General shape, we'll start with the end behavior, right? And so the end behavior looks like an even degree. So I guess my jumping off point is going to be, is n equal to 2? There's some activity in the middle, so I think maybe not, but let's see. Or maybe it is. Stay tuned. We need to figure out how many turning points. I have 1 turning points, 2 turning points, 3 turning points, right, where it kind of changes its mind. And so here I have 3 turning points, which means if it's allowed to have n minus 1 turning points at most, and I have 3, then n must be at least 4, right? And so here, therefore, n minus 1 equals 3 means that n is at least 4. So we scratch this, right? We had to bump it up a little bit. That's okay. Now, at most, n horizontal intercepts, well, that doesn't help us very much because it only has 2. Wait, what the? So it is. I'm confused. And that's usually not a good thing. These are turning points. In the 3.1 assignment? Yeah, because there's only 2 horizontal intercepts and we're allowed to have at most 2 horizontal. At most 4, and so we're allowed to have 2. Okay, phew. Okay, I'm gonna write that down. So 2 horizontal intercepts. We're allowed to have at most 4 if n is equal to 4. We're allowed to have fewer. Oh, phew. Okay. Yeah. I'm sold. I wouldn't blame you if you are not. But, okay. 2 horizontal intercepts is allowed if n is equal to 4. Because we can have at most 4, but that means we're allowed to have less. Allowed less than 4. So therefore, the least possible degree is 4. Nice. Okay. Okay. I'm torn. Do I start a new section? Quadratics? Or just parking lot it for Monday? Let's parking lot it for Monday. We'll do quadratics next week. It'll be fun, I promise. Quadratics are what? Hey, Emily, you were sounding like you were going to let us go, and then you're keeping us on the line. I know. It's my time. Quadratics are when we have the highest powers 2, right? So all of a sudden we're back to a power of 2 as the highest power. So degree 2 polynomials are what we're going to focus on next day. So next week, we're going to do quadratics, which are degree 2 polynomials and their properties. So we have f of x is something like a2 x to the 2 plus a1 x to the, x to the 1, but no 1, let's say 2, 0. Right. That's a quadratic, dealing with those, solving problems with those. Something to look forward to. All right. Stepping away from the plate. Enjoy your Friday. If you have any questions, let me know. Otherwise, I will see you on Monday.